All right, this is our warm-up. Take a look at this. Various packages with different masses are moving at a constant speed conveyor belt. At the instance shown below, all packages have the same constant velocity of 2 meters per second direction to the right. The packages do not slip on the belt. All masses are given in a diagram in terms of M, the mass of the smallest package. So the smallest package is M. The next one up would be 2M, so twice as big. Then there's a 4M, 4 times as big. There's also a 3M and a 5M. We want to rank the magnitude of the net force on each package. Rank the magnitude of the net force on each package. Take a look at that. Take a minute or two and get it done. I'll give you a minute to think about that while you do it. Okay, what do we think? I want some people to unmute, so I want most people to unmute. And I want you to yell out which package has the greatest net force acting on it. I'll give you a countdown. So first, everybody unmute. Everybody get a chance to unmute. I'm panning over a lot of names that still tell me you're muted. So yeah, I want to hear lots of background noise. Let's wake this party up. All right, background noise. Come on, everybody unmute. Let me pan around. All right, so let's see who this is. I'm going to ask to unmute. Ask to unmute. Come on, let's get loud. All right, that's almost everybody. All right, I'll take that crowd. Okay, so on the count of 1, 2, 3, yell out which one has the greatest amount of net force. 1, 2, 3. Let me hear you.
D.
Five.
D.
All right. So
And
keep
they're all
working until you get the. Wait, what was that?
Aren't they all 0?
Yes. Yes.
Okay.
Why? Why are they all 0?
Because the force they exert from gravity is like equaled by the normal, right?
Okay. Oh, so close. So close.
There is
Why
no
is it 0? Somebody give me a better answer.
there is no acceleration.
Yes, both of those things. All right, so he was right in the vertical, but these things are moving horizontally. And I had 2 people answer there at the end once it was established. But horizontally, how do we calculate force? Mass times what? Acceleration.
Yeah.
Is there any acceleration when these are moving at a constant velocity?
No.
No,
Oh,
there's
excellent.
not. All right, so very nasty trick. All right, everybody mute back. All right, very nasty trick question, because we know that the force is mass times acceleration, and this this problem told us that it was at a constant velocity. So we have a mass of 5m, 2m, 1m, that's fine, times 0, because there's no acceleration. So there is no net force. Now, are there forces? Sure, but they're balanced. And so when we take one force going this way and one force going that way, so they're going this way, but they're balanced. So you take one, subtract the other, you still get a net force of 0. And that's how you keep that constant velocity. So let's make sure we're sharpening those tools and not forgetting the things we just learned. Constant velocity, balanced forces. Balanced forces, equilibrium, equilibrium, net force is 0. All those things are equal to each other. I know it's crazy, but it's true. There's probably a song that has those lyrics, I'm sure. But anyway, we're not going there right now. So we've got our warm-up out of the way. We're going to do, let's take a look at the homework. So get the homework out. No, you didn't have to submit it. Yes, you had to do it. I know how many people did it because how many people asked me questions about it. So either you're really good at Googling or you ask me questions. So let me admit our last student of the day. He made it. And let me fix the roll because I already marked him absent. So let me unmark that. All right, welcome to class. All right, I'm marking you present. So now everybody's here today. All right, the roll is fixed. Let's look at forces and applications of Newton's first law. Together we did page 1. There was still page 2, 3, 4, 5. So let's share this. So that's why I'm looking at this other screen. Sorry, I know it looks like I'm looking away from you guys, but I don't mean it. There's the grade book. We can burn that when we need to. But for now, we're just going to look at this guy right here. All right, so let's do this. All right, so we did page 1 together, so that should be all filled in, right? Mine is, see. All right, so then let's go to page 2. I want to field questions, and I'm only going to do this based on student driven. I do need to watch the time because I want plenty of time to go through the test. If you didn't take the test, I'll tell you when to bug out of the Zoom and to come back at a certain time. So, but everybody needs to be here now. I've got something in the chat. Let's see what it is. Bam. What force were acting on the boxes? What forces could have been acting on the boxes since they're moving? There was nothing moving in the horizontal at that moment in time. We could say that the conveyor belt was moving it to the right and that friction was moving it to the left, and those things were balanced in the horizontal. So the movement of the so a force applied to the right because the conveyor belt was moving it to the right, and then friction to the left, and that's because that opposes movement. Those two things were in balance. We could say that. Okay, so that, I'm sorry, I got to that question a little bit late. I'm late to the game, but I am here. So I'm gonna move the chat where I can see it. I'm sorry, I'm rearranging a desktop. Bam, bam. All right, now I can see all the pretty faces and the questions. Now, if you get verbal, I'll address you first because I can hear better than I can read. But what questions do we have on this? Or did we blow through it? We said even the spring questions were easy. No, they weren't. So that's how I know if you did this or not. Did you get all the way to the spring questions? So ask questions, I will provide answers. Otherwise, we move on.
Mr. Watley,
Go.
I had a little trouble understanding number 11.
Number 11. All right, so let's scroll this up to number 11. All right, number 11 is the first place that most people bog down. If you kept working, which I'm glad you did, it brought us to number 11. There is a bit of information you need to answer this question beyond what we covered in class. A couple reasons for that. One, if we were in class, you would have done a spring lab and you would have had the information. Two, I didn't give it to you sort of intentionally because I want to know how far did you get? Because if I get no questions, I know no one's doing the work. So let's look at number 11. I'm gonna get my little stylus out and write all over this guy. All right, so it tells us when a mass is placed on top of a vertical spring, the spring compresses. Okay, so I'm gonna put 13.2 kilograms. I need a drawing tool. So 13.2 kilograms. All right, that's my mass, and it's sitting on a spring. So if you haven't done it, which I'm guessing is like all but maybe 2 people have not done this problem, get to this problem, or at least get to a blank sheet of paper, and let's look at this problem together. In this problem, we're gonna have to grab different bits of information that we know or that we're learning now and bring them together, which is gonna be common in this course. So we've got a 13.2 kilogram object sitting on a spring. It compressed at 5.93 centimeters. We know displacement is in meters. I don't give a rat's tail about centimeters. It's not relevant to me. I need this in meters. So I need to say that this is going to compress the spring. It's going to push the spring down, not 5.93, but instead 0.0593 meters. Now, if I'm getting my math wrong, you got to tell me. I'm doing this on my own right now, okay? So we've squeezed it down. Now, is this weight in motion? Got to talk to me. Is the weight in motion or is it resting?
It's resting.
It's resting. So if it's resting, could we say that the velocity is constant?
Yes.
And if we said the velocity was constant, could we say then that the forces are what? What would the forces be?
Balance.
Balanced, yeah. That's what we're looking for. So that means that force of gravity going down, because we're on Earth, is going to be balanced by the spring trying to push that weight off of it, right? So we have a force of a spring, because we did say this in class, that springs are a contact force. And if we compress them, they try to push back out. They want to be at their equilibrium. And if you compress them, they push out. If you stretch them, they pull back in. So we know that the spring is pushing upward on the weight and gravity is pushing downward. We said that the velocity is constant, 0, but it's constantly 0. And that means the forces are balanced. The force of the spring and force of gravity are equal. So we can't really solve for the force of the spring yet, but we could do gravity. So that's a good first start. So let's say that the force of gravity is equal to mass times acceleration. For gravity, okay, we can do this. Mass is 13.2, and that's times 10, because that's the acceleration of gravity, right? So then the force of gravity would equal 132 newtons, yes? So we know that gravity is pushing down at 132 newtons on our object. What did they say what it was? Just as a mass, so it's an object.
Mr. Watley,
Yes.
would
What's
that
up?
be the weight?
That is the weight. Yes, the weight, the force of gravity, those are the same things. Yes, absolutely. Good question, because sometimes it'll say weight and you'll think it's saying it's meaning mass, but it's force of gravity. So this is the weight and it's balanced by the force of the spring. So we know force of spring is equal to the force of gravity because we said balanced forces, and these are the two opposing forces. They're balanced, so they have to be equal to each other. Now, this bit of information you didn't have in class, so I'm going to write this down. The force of the spring is equal to the spring constant times the displacement. This is called Hooke's law, and it's saying that the force of the spring is the spring constant, negative K. Now, it's not negative spring constant, it's negative K. That is the spring constant. And when it's negative, because it's trying to return itself to equilibrium. So just, if you want to just make it K, that's fine with me, because you're not solving for that. You're not getting rid of the negative. It's just called negative K. That is the constant times how far it's displaced. Now that constant is constant for any particular spring. So once you solve for one spring, it doesn't matter what you do to that spring has a constant, unless like you heat it up or you overly stretch it to where you break the spring, okay? So as soon as you know the constant for a given spring, it's constant. Now, if you get a different spring, different constant. I think we're on the same page right now. So if we know that Fg is 132, that means Fs is 132. So let's fill that in, 132. That's equal to the constant times the displacement. And we said the displacement is 0.0593. So if we divide both sides by 0.0593, 0.0593, let me get my calculator out, 132 divided by 0.0593. We get 2,225.969646. I'm just going to call this 2,226. I'm a rounder, and I'm going to round. So 2,226 is the spring constant. Perfect. We know the spring constant. Now, what they say happened next? Now we're going to put a different weight on, or a different mass onto the spring. So now we have a 17.2 kilograms on the same spring. And we want to know the displacement, right? Okay, well, the force of gravity for this guy is equal to 17.2 times 10, which would equal 172 newtons. We know the spring's not moving right now, so it's balanced with the force of the spring. Force of gravity, force of spring, they're in balance, they're in harmony, they love each other. It's Friday, so they're getting along, because that's what we do on Fridays, right? So force of the spring is equal to the constant times the displacement. In this case, the force is larger because the force of gravity is larger, so we've got that 172 is equal to the constant. We said the constant was 2226 times the displacement, which we don't know. Divide both sides. And I get 172 divided by 2,226 equals 0.077. So I'm going to call that 0.08 meters equals my displacement. Now, you did get a new formula. It's Hooke's law. It is on your formula chart. It is legal to use and have access to during any test or quiz. Force of the spring is the constant times the displacement. Now we're using Newton's second law, or well, it's still in Newton's first law, I guess. But we're basically saying balance forces. So Fg is equal to Fs. So we can solve for Fg, that gives us Fs. They told us the displacement, we got the constant. And we just worked that for a second weight. Okay, so I've got two things in the chat. Can I do number 6? And could I go over 14? So yes, we still have time. So I'm going to scroll up to 6 and then back down to 4. What's up?
I have a question.
Yeah, go for it.
How'd you get the 0.0593 from the 5.93?
Because they told us 5.93 is centimeters and I need meters.
Oh,
So I divided by 100.
All right, yeah.
Wait, so for each spring, the constant's the same?
All right, for a given spring, for that spring, let's pretend my stylus is a spring, and let's pretend this is another spring. This spring will have a constant. This spring will have a different constant.
Okay.
But it doesn't matter what weight I put on either one, they maintain their constants. And even if you bought 5 springs from Home Depot in the same bucket, and they're all supposed to be the same, they all have different constants. It would take a very accurate laboratory to create springs that have the exact same constants, because it's the tightness of the coil, it's the type of metal that's being used, it's how many coils does it have total, and are each one exactly the same? You're going to find some differences. So for a given spring, it is constant, but as soon as you grab another spring from a box, it's different.
Wait, so since they mentioned same spring, we can use the same constant.
Exactly right, because they took the weight off and put a new weight on. So the spring was the constant was constant because the spring was constant. Using too many constants this morning. I'm sorry.
All right, thank you.
I'm trying to make somebody smile and laugh. I got like one smile, and then it seemed like you responded a little bit. So there you go. All right, so let me erase.
I have another question, real quick.
Go for it.
Do we always change it to meters? Like
Yeah.
if it's in anything other than that?
Yes. Mass, you always want kilograms. Meters, our distance displacement, you always want meters. Of velocity, meters per second, acceleration, meters per second squared, time seconds. Yes.
All right.
There's a particular unit for every measurement, and we want to get to that unit most of the time.
All right.
I'm going to wipe this out just so second period and fourth period don't get to see all the beautiful work. It's gone. All right. So in order, I had number 6 requested. So let's go up to number 6. All right, Rocky the Flying Squirrel's gliding from a tree to the ground at a constant 3 meters per second. Now in this case, I see this word constant, and that's what's important to me. I do not care about his meters per second, his velocity. What I care is there any acceleration? It said constant velocity, no acceleration. That means forces are, say it out loud, forces are?
Balance.
Balance, yes. Thank you for playing along. All right, so his mass is 200 grams. 200 grams would be 0.2 kilograms. So 0.2 kilograms. How much air resistance is acting on Rocky? Okay, well, we know that air resistance would be going up, and I know air resistance doesn't exist in this classroom. We're not calculating air resistance with some air resistance formula. We're just balancing forces. So it's okay that it's here sometimes. You just have to, you know, accept it, I guess. All right, so I'm gonna put AR for air resistance. And then going down, I'm gonna put force of gravity. And those forces are gonna balance each other because of constant velocity. Well, force of gravity is equal to mass times acceleration, which would be 0.2, that's a 0, times 10, which equals 20 newtons. And since force of gravity is equal to air resistance, ooh, that should be just like air resistance. That means 20 newtons is equal to air resistance. How much air? Why did they say 1 point? Oh no, I'm dumb. I'm so dumb. Why didn't y'all stop me? Bad math. 0.2 times 10 would be 2. And that's also 2. See, I make mistakes too. I would totally mess up on y'all's test just like y'all do. Because we're all human. All right, so in the X direction, we've got nothing. In the Y direction, we can say is equal to Fg minus air resistance. If we wanted to use numbers, that's 2 newtons minus 2 newtons, which is equal to nothing. The sum of forces is equal to 0 because we have balanced forces. How does number 6 look? All right, and if you saw that I did the bad math, you should have laughed at me out loud, okay? Don't just laugh at me in your room. You've got to unmute and laugh at me, all right? I wish I could keep track with anybody that discovers a mistake I do and give them a point. If I could do that, I would be totally in on that. All right, so.
So you're saying, Mr. Watley, that since it's a constant, there is no acceleration, therefore, it doesn't like add up to anything.
Right, because if we have a constant velocity, there's no acceleration. No acceleration means my forces are balanced. And that if the forces are balanced, when I add them all up, I get 0 because opposing forces subtract. And if they're balanced, anything minus the same value is back to 0. So in order to have a net force of something, there's gonna be some acceleration. There's gonna be. And so right now we're starting off easy. Okay, let's admit it. We're starting off kind of easy because everything's balanced. That just means this is getting us used to the environment, but it's gonna get more challenging. So don't worry, you'll have some challenges coming up. That's not meant to scare you. That's just meant to be like, cool, it finally gets exciting.
Mr. Wiley, can you do a problem where there's not a constant velocity?
Is there any on this sheet? Do y'all remember? We're gonna get to it. We're gonna get to it. Let me scroll up to number 14 because that's the last one that's in the chat. But if you find one in this sheet, I don't want to scare people that are barely holding on because it's not bad. But I want to make sure that we're kind of secure in what we're doing first. So number 14. All right. A student with a mass of 70 kilograms. Okay, so 70 kilograms. I'm going to use their little box here on the side. So 70 kilograms jumps into a swimming pool and sinks to the bottom. What is his weight? All right, so weight is, all right, let's put this, weight is equal to the force of gravity. They're one and the same thing. Force of gravity is mass times acceleration. For gravity, acceleration is 10, so this would be 70 times 10. So force of gravity would equal 700 newtons. All right, so I got that because they use 9.8, they got 686, so we're cool. If the buoyant force, okay, so if you've never been around water much, buoyancy isn't something that you're used to hearing. But buoyancy is what pushes things up in water, makes them float, okay? Yes, density has a lot to do with it, but the actual pushing of it up is the force, the buoyant force, okay? Do you need to memorize it? No. Do you need to be familiar with the term? Let's say yes. Let's just be familiar with the term. So the buoyant force, you've got gravity and weight pulling you down, but buoyancy pushing you up, okay? So if we said buoyant force is 653.33, so I'm gonna do an arrow up, and then force buoyant, how about that, FB, is equal to 653.33, and then we've got force of gravity equal to 700 newtons. What is his apparent weight in water? Okay, well, his apparent weight in water would be what? I'm going to cheat. Let's see what I did last time. 14. What is his weight? What is his apparent weight? That's such a weird question. What would his apparent weight in the water be?
Hey, Mr. Wiley, isn't that just like the force of gravity subtracted by the buoyant force? Like they're looking for like the net force or something?
Well, this is going to be tricky, okay? This is sitting on the top of the water, right? It's floating. This person's floating. They're at the top of the water. So if they're at the top of the water, they're on the surface of the water.
It says he
Sink
sunk.
them?
It says he sunk. He sank.
All right, he floated. Go with, he's sitting on some water, right? There is some bit of, he's not dry on his butt, is he? There's some water on his bottom. So he's sitting on at least a little bit of water, yes? Okay, so just go with this. All right, he's sitting on at least this much water. He's floating on this much water. Yes, the buoyant force is exceeding his weight, so he did go down, but he's sitting on at least a little bit of water, just a little bit. And that little bit of water would be a surface, right? So that little bit of water is pushing up on him. Otherwise, it would get out, he would just hit the concrete and it would be dry. Between his shorts and the concrete, it would be dry if he pushed all the water away. But there's at least this much water, a tiny bit. So that tiny bit of water does give him a normal force, yes? Okay. And then is he moving when he's sitting down there? He's at a constant zero, right? So we have to have some balance of forces. So that normal force would have to be what, 46.67? Let me make sure I'm doing that math right. Yeah, 46.67. And yes, these numbers are going to get off because they're using 9.8. But this would add up correctly for me. Okay, so don't look at their answers too much. But that little bit of normal force. Now, why are they saying that's his apparent weight? This is a tricky question that deserves an explanation, but why would that be his apparent weight? If you ever pick up somebody underwater, aren't they really light? But then you try to get them up out of the water and they become a lot heavier? Okay, so your apparent weight comes from your normal force. Okay, it's the amount of force it takes in order to push something upwards, right? The buoyant force here is helping take the perceived weight away. So the buoyant force is already pushing upwards at 653. His weight is 700. So in order for you to make him float or to push him up, you just have to balance the force of gravity, the weight. You just have to balance that out. You're already being helped with 653. You've got 700 going down. You only have to push up with 46.67. Anything more than that, you're going to accelerate upwards. It's a really weird question, but I want to give you a real world example that's going to hopefully make a little bit more sense of it. So forget this problem just for a minute and let's have a small conversation, okay? You guys ever had to stand on a bathroom scale? Tells you how much you weigh, right? It's in pounds, and pounds is a unit of force, but we don't use pounds because in physics we use newtons, okay? But it's both of them weigh or measure weight, correct? Because weight is a unit of force. We said that force of gravity is weight. Weight is a force. All right, so I think all of us have at least stood on a scale at some moment in time and either been happy with it or sad at it, but either way, we've stood on a scale, right? Now, what is the scale measuring? What force is the scale measuring?
Gravity.
Anybody else want to agree? Only one brave soul?
Your math.
The force you
after-
exert on it.
All right, so it's not measuring mass because mass isn't a force, but it's definitely measuring a force. So what are you saying now?
Force of gravity for weight.
All right, most people are saying force of gravity. Does anybody want to oppose?
The force of gravity on your mass.
Okay, okay, still, I would categorize that the same way. So everybody's still saying force of gravity. Does anybody want to oppose that answer? Anyone want to be brave?
Could you repeat the question?
What force does a bathroom scale measure?
Okay.
Okay, let's,
Maybe-
let me ask a different question. Does the force of gravity on you ever change when you're on planet Earth? Because your mass certainly is not going to change. I am my size. Unless I go on a crash diet and it changes over time, as long as I'm sitting here during first period, my mass is not changing. Okay. Now, is the acceleration of gravity changing while I'm sitting in this classroom?
No.
No, absolutely not. And if it did, we'd have bigger problems than the questions on this worksheet, right? So force of gravity, acceleration of gravity is not changing. So we could say that while we're on planet Earth, force of gravity is on me or on you is constant for me or for you, right?
Yes.
Okay, I just want to lay a foundation. Those are not trick questions. So if a bathroom scale measures the force of gravity, that means no matter where you stand on that scale, it should give you the same answer, correct? Do we agree?
Yeah.
Yes.
Okay. All right, I'm boring only one person so far, it looks like. No yawning that big. Come on, girl. All right, now let's say this. What if you got on an express elevator in downtown Dallas, and it was a 100-floor building, and you're in the lobby, and you shoot up to the 100th floor? Don't you feel really heavy?
Yes.
And then once you get to the 100th floor, what if you press lobby and you shoot all the way down 100 floors in 3 seconds and stop at the lobby? Don't you feel really light?
Yeah.
And wouldn't that scale measure something different when you're feeling really heavy and when you're feeling really light?
Yeah.
Yeah.
So is it really measuring the force of
Mr.
gravity?
Watley, is it the force the scale has to exert on you to maintain
Yes.
like,
And what is the name of that force?
Normal.
balanced force?
Normal force.
Oh.
Absolutely right. A scale measures normal force, not force of gravity. A scale measures normal force. It measures how much does it have to push up on you when you're pushing down on it. Because if you go into an elevator and you're shooting upwards, you're going to push a lot harder down on that scale. I take that back. When you shoot up in an elevator, the floor of the elevator has to overcome gravity and push up on you really hard. And that's same for the scale. If you're on the surface of the scale is going to have to push on you really hard for you to accelerate upwards. Now, once you're up on the 100th floor and you're going to go down, just like a ride at Six Flags or Disney World or whatever, if you want to go down really fast, you need to reduce your force normal so you can go down. So the scale then reduces the force normal. You fall down or you go downwards with a reduced force normal. When you go up really fast, you have an increased force normal pushing you up. And that is why a scale is measuring force normal, not force of gravity. So let's bring it back 360 and see if I can apply it to this question. When you're pushing up on somebody, that is a force normal. So you're only having to balance, say you're pushing them up at a constant velocity, you're only having to balance the forces acting. You already have buoyancy helping you. And that is why it's easy to lift someone in water, because they still have the same weight. They still have the force of gravity, but their buoyancy is helping overcome the force of gravity. It is aiding you in the pushing up. That's why once they get up out of the water and you're trying to make them do a backflip up around you, you get up out of the water and you're like, dang, now you're heavy, boy. But then when they're underwater, it's like, oh, I got this, right? So that buoyancy is a force that's going up, and then their perceived weight, it says perceived weight, and the perceived weight is kind of like a scale. It doesn't know your weight. It just knows how much it has to push up on you. It's a perceived weight. Now, if you're not moving, it's all in balance. It's the same thing. No one knows the difference. But if you're moving with an acceleration, it's different. And that's why we talked about the elevator. I hope I only confused 7 people, but the rest of the 33 were like, I totally get this. For those 7 people, I totally apologize. And I'll tell you that this recording will be on Zoom sometime today. And you can repeat this exercise over and over and over again until you're outright confused. Then email me and I'll confuse you more. No, I'm just kidding. I'll try to clarify it. All right, so we've done 14. I'm going to erase this real quick because it's in the way and I don't want second period to see it before we do it. I kind of want to get into the test. Is there anything in here that we absolutely want to see before we do a little test review? Okay, so I see a lot of shaking heads of no, so that's awesome. Let me stop this share. Okay, so now we've finished the review. Don't ask me questions about the test right now because I've brought someone back in that has not taken it yet. If you have questions specific to the test, I want to have you guys contact me about questions. If it's about your grade and you just absolutely need more information, then let's set up an individual Zoom or come to tutorials and we'll just work through it in tutorials. You'd have to pick my tutorials to ask about your specific test. If it's generic about the test, you can go to any tutorial. Anybody can help. When are you, okay, so retest. I have unlocked the kinematics multiple choice questions in College Board. Go to College Board, take the multiple choice questions and do them to the best of your ability. Once you have finished those, you are then eligible to retest. Retest is opened Tuesday, Wednesday, and Thursday of next week from 8 a.m. to 9 a.m. and from 4:30 to 5:30. There are 2 retests. You don't have to take them both. Just take the one or ones or both that you need, and you can retest up to an 85. I've already put the grades in for the test, and I have updated your original quiz grades for the test grade replacing quiz grade. If I updated your quiz, you'll know it because it'll have a decimal point. Let's say you made a 50 on the quiz, but you made 100 on the test, or let's say you made a 90 on the test. Your new quiz grade would say 90.50. So that way we would know your original quiz grade, but you would have it replaced by the test grade. So yes, the quizzes have been replaced. Now, if I am not perfect, and if I didn't replace yours and I made a mistake, let me know. It happens. I make mistakes all the time. So you've got, if you do the retest before you do the College Board multiple choice questions, I will throw out your retest. You are ineligible. The College Board thing is open. It doesn't close. So it's available to you to do at any time, but retests start Tuesday, go through Thursday.
Mr. Watley, do you have a code for the classroom? I didn't write it down the day you gave it to me.
Why? Why would you do that? Okay, I'm just kidding.
Sorry.
Let me see if I can get the code for you guys. It'll take you just a second. Pull that up. As soon as we get done with that discussion, let's go into the assignment for today, which is the Newton's second law practice. I want to do at least a little bit with you guys, as long as we can get to that. But let me see if I can log into College Board and get you that code. All right, sign in. Submit. Yes, and if you have not registered for College Board for our class, I'm going to put the code in the view join codes for 3 seconds. I'm going to put this in the chat. You have to get into our College Board. All right, so let's type this in. It is MZM 37K. 37K. All right, that is the course code in College Board for our AP1 class. MZM, Mary Zulu Mary, 37K like kilo. All right, so now I'm going to go back to this Newton's second law practice. All right, does the College Board multiple choice say Unit 1 process check MCQ? Yes, it does. So I'm actually going to try to highlight what you said. I'm trying to copy and paste. Or here, let me just say it. The College Board, it'll say Unit 1 process check MCQ. That means multiple choice questions. We'll be taking the retest on a Zoom call. No, you won't. But that does not mean you're taking it on FaceTime, text messages. How else do you communicate? WhatsApp, all those things. This is still a test. It's still a test. But I want to make sure you have ample opportunity to take it. And I'm just not going to be available for 6 times for retesting. So you're going to have that time, but you are still being honest with yourself, with your peers, and with me. It is a test for you. Right before we start the next thing too, I have the drop link for AP1. It's available starting today through next Friday. Look at your grades. I'm going to send out an email over the weekend to everybody. All right, someone's trying to come in through their phone. Oh, that's risky. Oh, they're gone. So good. I didn't admit them. Okay, so I'm going to send out an email over the weekend, and it's going to go to everybody. So if you have a 90, or even if you have a 78, and you're like, why is he telling me to drop? The message is going to go to everybody, but I'm going to ask that you do this. You take a hard look at your grade, how hard you're working, how much volume I'm giving you, and can you keep up? Are you going to make adjustments so that you can continually improve in this class? If you can't say that you're going to do all those things, I honestly hope if you drop the class, you end up in my on-level class, because I want to see you guys and keep working with you guys. On-level's no joke. Every time I have students go from AP1 to on-level, they struggle because they think they're walking into a class that's a breeze. Physics is still physics. So it's still work, but the intensity is not going to be there. So if you've taken on too much this year, you need to start thinking about that this weekend. And I'm going to try to send out a note probably on Saturday. I'm going to provide the link to everybody. And I need you to ask yourself, are you going to be successful here? All right, enough about that. Now let's keep working. Let's get into this next thing. So today's homework going into the next class, today's Friday. So for Tuesday, I want to have this worked as best you can for Tuesday. If you have trouble, you're going to email me. You're going to ask for Zoom meetings. You're going to talk with me and communicate with me as you struggle, if you struggle. So let's share this to here, share. All right, practice Newton's second law. And let me get the right thing in front of me so I've got some sort of orientation of what we're doing. You should see this desk, it's a mess. All right, let's see what we have going on. Wow, this is like work, actual work. All right, let's see what we have. A 20 Newton horizontal force gives a stone on the ground an acceleration of 4 meters per second. Oh, this was asked about earlier today, wasn't it? What is the weight of the stone? How far will the stone travel in 12 seconds if it begins from rest? Okay, you guys asked for some things that didn't have balanced forces. So let's see what we have. A 20 Newton horizontal force. Okay, so that means, let me get my drawing tool. I have a, let's just call this a force applied equals 20 Newtons. I'm putting you don't necessarily are supposed to put the forces on the free body diagrams. I'm doing this for my notes. I'm doing this for teaching, but as you get used to this, just put the forces on the free body diagrams, and the values you can put somewhere else, like in a legend that says FA is 20 and all of that, just kind of giving you some orientation. All right, so now it's on the ground, and I'm gonna guess it's on Earth. So we're gonna have a force of gravity, and we're gonna have a force normal. And it's moving along the ground. So we know that it's not accelerating vertically, right? It's not hovering, it's not shooting through the ground. So some things we know is that force of gravity is equal to the force normal. Those are equal to each other because we're balanced in the vertical. In the horizontal, let's see what's going on. What is the weight of the stone? How far will the stone travel from rest? Blah, blah, blah. Okay, so what can we do? Well, we know that force is equal to mass times acceleration, correct? Okay, and then they said that the force was 20 newtons and the acceleration was 4. So we could rearrange this equation to solve for mass, couldn't we? We could do that, right? So let's divide both sides by acceleration. And we would say that force divided by acceleration is equal to the mass. That's just simple algebra using Newton's second law. Force is mass times acceleration. Now they told us the force was 20. They told us the acceleration was 4, and that's going to equal the mass. 20 divided by 4 is 5, so 5 kilograms is equal to the mass. So I'm going to put that up here in my free body diagram. I'm going to say 5 kilograms.
Mr. Watley,
Yes.
did you just say the weight is 5 kilogram? Oh, you said the mass is.
Yeah, the
But
mass
then
is
why
5.
is it asking for the weight if we know it's 20?
Times force of gravity.
Oh,
Right.
okay. It's okay. I see now. I see what's going on.
So I'm going to scoot over here. I'm going to say weight is equal to the force of gravity. Force of gravity is equal to mass times the acceleration of gravity. And we know now the mass is 5 kilograms times 10 meters per second square. So the force of gravity in this case will be 50 newtons. I'm going to put that in my picture just to kind of keep things together. So 50 newtons. Again, I'm putting the values in the picture so that you can see it and understand what I'm doing. Your free body diagrams should just have the forces, and you should be putting the actual numeric values outside of the diagram. Now we said that the forces were balanced, right? So then the normal force is also 50 newtons. So it asks us, what is the weight of the stone? Well, we got the weight, so we're done with that one. I'm gonna check that off. How far will the stone travel in 12 seconds if it begins from rest? What does that sound like?
Kinematics.
Kinematics, exactly right. So if we come over here and they're telling us time is 12 seconds. Time equals 12 seconds. It begins from rest, so V naught equals 0 meters per second. It wants to know how far will it travel, so it's going horizontal, so delta x equals question mark. And then we know the acceleration is equal to 4 meters per second squared. So we can use an equation that has, what is it, delta x equals V naught t plus 1/2 AT squared?
Yeah.
Okay, so go ahead and write that equation down. Delta x equals V naught t plus 1/2 AT squared. And you've got everything you need in order to, you don't have to rearrange the equation because it's already solved for delta x, but you can plug in what you have. V naught t will go to 0. So you just need 1/2 AT squared. So 1/2 of A would be 2 times 144. So 144 times 2 would be 288.
Yeah.
And look at that. That's what they got as well, 288. Now, this is still bringing in some kinematics. Don't worry, we will not drag kinematics through the entire year. It'll feel like it for a little while, but at least when you're doing it now, you're like, I got this kinematic stuff down. So bring it, right? We've totally got this. And all we're adding is force is mass times acceleration. That's not hard. We can do this. We can totally do this. All right, y'all want to do one more and then let you take off and finish it up? All right, let's do one more. Let me scroll this up. A 5-kilogram rocket is acted upon by a force of 59 newtons due to the thrust produced by its engines. What is the rocket's weight? What is the net force? What acceleration does it cause? Wow, that is a lot of questions. Okay, let's take this one bit at a time. All right, so 5 kilograms, put that in the box. It's by an upward force, so this is going upwards, and we're gonna call this thrust. And it equals 59 newtons. Okay, and by its engines, what's the rocket's weight? Well, we know weight is Fg, and Fg is mass times acceleration, right? And acceleration of gravity is 10, so Fg would be 50 newtons, yes? Okay, we've got this. Now, let's not forget sum of forces is mass times acceleration, right? So my sum of forces in this case, let's see, what am I solving for? All right, what is the net force? The net force is the sum of forces. They went off, they wouldn't turn on for me because it's like they're pointing that way. So I was all like, oh. All right, so the sum of forces is gonna be 59 newtons minus 50 newtons. That's my sum of forces. So I should put like sum of forces equals. So my net sum of forces is 9 newtons. What'd they get? Let's see, what's the rocket's weight? 49, we got 50, perfect. Net force, 10 newtons up. We got 9 newtons up. What is the acceleration does it cause? Okay, we can still do this because we know the sum of forces equals mass times acceleration. We're looking for acceleration, so we're going to divide both sides by mass. So we would say that sum of forces is 9 newtons divided by the mass of 5 equals acceleration. Do not give me, oh, that's another thing. If you gave me a fraction on the test, I took points off because I told you guys decimals. Decimals, there's too many fractions that equal the same decimal. 9 divided by 5 is 1.8. So the acceleration is 1.8 meters per second square is the acceleration, and it's going upwards. All right, these, even though the equations are easy, force is mass times acceleration. Net force is mass times acceleration. Sum of forces is mass times acceleration. All of a sudden, it becomes a little bit more complicated. You've got to draw the picture. The free body diagram is going to be your guide. And then you just kind of work it one bit at a time. What can I solve for first? All right, there's something in the chat, and then we're going to call it a day because they're about to start talking over the speakers. Could you go back to number 1 real quick? Absolutely. What I'm going to do is I'm going to scroll this down, and I'm going to see if you can see both of them at once. Yeah, you can. All right, so there's number 1 and 2 simultaneously. All right, I'm only going to share this for just another minute. I'm going to start packing my things up. You're going to communicate with me when you get stuck. You're going to work all the way through this packet. Watch for my email on Saturday. And I want you to think about those questions I send you. How are you doing in this class? Is it working well for you? Are you keeping up? Are you doing well? If not, can you make the changes needed to be successful? And if not, are you willing to make that difficult decision and say, this isn't the right place for me right now, okay? I want you guys to stay, but I also want you to be happy and productive. And if you're not doing well and you can't make those changes, you will not be happy or productive. All right, were you able to find more information about whether or not we have another test this 9 weeks? No, because I wasn't here yesterday. I was out of town yesterday attending a funeral and I did not get that information. I do meet again today. As soon as I have that information, you will know it. As soon as I have that information, you will totally know that. What values would we fill into the table? For the table, we would say that for the X direction, there's nothing. For number 2, in the Y direction, we would have thrust minus FG, or 59 minus 50. In number 1, in the X direction, we would just have sum of forces is equal to the force applied or equal to 20 newtons. In the Y direction, we would have force normal is equal to force of gravity, or force normal minus force gravity is 0. Oh, it's totally okay. I appreciate the sentiments. The person had lived to 95 and a half years old. And so they lived a good long life. So it was a good time to see family together for a full day. So, but thank you for that comment. Anything else? I can do anything last minute until they start talking on the speaker, but the speaker we'll call that the official end.
Wait, where can we find tutorial timings or schedule?
If you go into our class, as soon as you go into our class, you have an option for like teacher info or course info, or like the course. Click on the teacher info. In there,
Okay.
there's a calendar and it has like days and times. You click on the current day and time and that puts you into the Zoom. So now that's the end of our class.
All right. Thank you.
And I'll talk to you guys soon. If not sooner, I'll see you guys on Tuesday.